What is DEM? DEM stands for the Discrete or the Distinct Element Method. It can be precisely defined as a particle scale numerical method for modeling the bulk behavior of granular materials and many other geomaterials like coal, aggregates, pellets, tablets, soil, rocks, and of course powders as well. The method can also capture the dual nature of materials, reproducing fluid and solid characteristics of the granular flow. It is a simulation of discrete elements. The method has already been applied for many applications in the fields of pharmaceutical, process engineering, mechanical engineering, material science, agriculture engineering, and many more. It is a mesh-free method and does not solve the continuum equations of motion. It has the ability to numerically calculate the finite particle displacements and rotations and automatically perform contact detection from an assembly of particles. The equations of motion for every individual particle are numerically integrated with time for which the total force acting on the particle needs to be known. Now there are two methods for discrete simulations. One is the hard sphere approach while the other one is the soft sphere approach. The left side of this figure is showing the hard sphere approach while the right side of the figure is showing the soft sphere approach. In the hard sphere approach, impulsive forces are allowed, exchange of momentum is possible, but only one collision of particle is possible at a time. While in case of the soft sphere approach, rigid particles but small overlaps are allowed, means that the particles are rigid but small overlaps are allowed, and that is only because to calculate forces accurately. And simultaneous contacts are also possible in the soft sphere approach. Now, the soft sphere approach is also the most accurate commonly used approach, and it is also the main theme of the discrete element method. Reason being that the approach is capable of evaluating interaction forces very accurately. Also, the approach is used in the EDEM and Rocky software as well. Now, let's compare the DEM and DPM methods, the discrete particle method and the discrete element method. DEM is a method in which each particle is tracked individually, while in contrast to the DPM, in which is a parcel-based approach, in which a group of particles are tracked at a time. DEM is based on the soft sphere approach, while DPM is based on the hard sphere approach. DEM is best for both dilute and dense flows and gives more accurate results, while DPM is only best for dilute flows and gives satisfactory results for dilute flows. And means DPM cannot be used for very high concentrations of particles, while DPM can be used for low and high concentration of particles for both dilute and dense flows. Now moving towards the DEM methodology, starting with the DEM algorithm, it uses the following general algorithm. For the process, each individual particle, the DEM program does the following. It locates all the neighboring particles and boundaries with which the particle comes into contact and calculates the sum of forces and moments acting on the particles using the Euler equations of motion given by this simple equation, which is a summation of the body forces and the surface forces. Now the body force is obviously the gravitational force, while the surface forces includes the contact forces plus the fluid particle interaction forces. Putting these equations into the first equation, we get the final equation, which is the equation used for the calculation of the translational motion of the particle. For movement, DEM program uses the current particle position, velocity, and the time step information to move the particle to its next position or location in the simulation. So based on these equations, we can calculate the new particle velocity and the new particle position, in which it can be seen that the time step information and the sum of forces acting on the particle is necessary. Also, these two equations were quite similar to the first and second equations of motion. Now, the EM workflow, as can be seen here, that the contacts between, if a particle comes in contact with the fluid or another particle, the forces acting on the fluid can be used to calculate the acceleration, and based on those accelerations, the new velocities and positions of the particle can be calculated. and the DEM cycle continues based on the Newton's laws and contact mechanics. Now, DEM-CFD coupling, it's a promising approach, the coupling of the Lagrangian and the Eulerian methods. There are two strategies, the one-way coupling or two-way coupling. One-way coupling is normally responsible for dilute flows, while two-way coupling is for dense flows, in which we have to study particle-particle interaction, while in one-way coupling, only we can study the effect of fluid on particle flow or simply the dilute flow. Well, in case of two-way coupling, we can study particle-particle and particle-fluid interactions. Now, why we use DEM-CFD rather than the CFD coupled approach alone? Now, let's move towards the advantages. In contrast to the continuum methods, the motion of every particle is simulated taking into account particle-particle interactions in DEM-CFD. And it's possible to deal with non-spherical particles even of regular or irregular shapes. No limitation of particle size concentration and particle size distribution is easily prescribed without increasing the computational cost of the CFD solver. Also, particle-particle Walls heat transfer and convective transfer, heat transfer with the fluid can be included in the DEM-CFD coupled approach rather than the CFD alone approach. Also, DEM-CFD is also based on the obviously discrete element method and CFD. In the Fluent, we use only the discrete particle method, and all the two methods are previously compared as well. Now moving towards the Rocky DEM particle simulator. It's a simulator which can be downloaded from the is easily available on the internet. The crack version can be downloaded. The present project is based on a crack version. It's basically a licensed software. Now I'll explain the parts of the software, starting with the physics. In the physics section, we can change the gravity, momentum, thermal, and coarse graining related to the particles as well. In the physics section, the gravity in the x, y, z direction can be changed. Also, we can adjust the gravity start and stop timing settings in this. In momentum section, there are many models related to particle-particle interactions and like rolling resistance models, restitution models, adhesive force models, tangential force models, normal force models. Each and every model is suited to any specific kind of situation. Mostly they are related to particle-particle interactions. Also, there is a section of modules in which there are these subsections, and I'll explain these now in detail. Now, the boundary collision statistics, it's used for analyzing the collision of particles with the boundaries, while the intra-particle collision statistics is used for analyzing the collision of certain particle shapes between two time steps. Intergroup collision statistics is used for analyzing the energy losses of particles with different shapes during collision, while the interparticle collision statistics is used to expand the collision of data of intraparticle collision statistics. Now, let's move to the next slide. Now, the geometry section. In the geometry section, we can introduce, by default, there are some geometries present, but normally we have to import our specific geometries like this, and it only performs geometry meshing on the boundaries. And as can be seen, it's a mesh-free method because there is no meshing inside the geometry, but only the boundaries of the geometry. So we can, if we want to study DEM-FE analysis, means the particle interaction with the geometry, so we can use in that particular case, we can use the boundaries as well. In this section of the materials, we can define material properties like Young modulus, density, thermal conductivity, specific heat, and Poisson's ratio, and properties of particles, boundaries, geometries as well. While in the section of material-material interaction, particle-particle and particle boundary interactions can be defined, and obviously particle boundary interactions are used for DEM-FE analysis. In the particles tab or in the particle section, these particles are by default present in the Rocky software. Also, we can import specific particle shapes related to our specific cases in a particular format known as STL, the standard tessellated language. And those particles can be made in any kind of CAD software like ANSYS Design Modeler or ANSYS Space Claim, SolidWorks, or AutoCAD as well. Also in the particles tab, the shape and movement, size, orientation and breakage composition of the particles can be adjusted. So in this software we can also study the breakage of particles, the particles at different orientations. Also the movement of particle can be adjusted. In the composition section we can define single element or multiple elements. Means we can define a particle into a single element, say as a single particle or a particle with multiple fragments. If you want to break the particle into multiple fragments, for example in 100 fragments, so we can define it to be a particle made up of multiple elements. So composition is used for that. Now this is a comparison of Rocky with the DEM standard codes. As can be seen that by using coding we can create a shape, but by using the glued sphere approach, and it's not that much accurate as the sharp edges approach of the Rocky software, in which we can study both regular both glued both type of particles based on the glued sphere approach, and also the regular smooth surface particles as well can be studied in the Rocky software. In the inputs tab we can introduce particles in the geometry, and there are two methods for that. One of them is the continuous injection, which is used to introduce particles from an inlet continuously from an inlet, while volume fill is used to introduce particles at specific positions, and we can define those positions manually as well. Now in the CFD coupling section there are normally three strategies in the Rocky software. One is airflow, which is based on the lattice-Boltzmann method, in which a lattice is created based on and airflow is generated by the Rocky software itself, in which air is the fluid. In the one-way coupling there is a constant one-way coupling option and Fluent one-way steady state. Fluent one-way steady state is the DEM-CFD couple approach, in which we couple Rocky with ANSYS, while constant one-way is an approach in which Rocky introduces a fluid with the specific density by its own, but it's not a very accurate approach. So DEM-CFD, obviously the Fluent one-way steady state is the better approach, while in case of the two-way coupling it's used for dense flows, for multi-particle, particle-particle and particle-fluid interactions, and it's also a main function of the Rocky software as well, in which we can couple the DEM-CFD as well also. In the domain settings, it's also a section in which we can adjust the minimum and maximum dimensions along with the periodic boundary conditions if they are present, or if they are needed in a particular simulation or in a particular case. Now moving towards this simulation case of my own research project. It's based on the dilute flows, means the fluid particle interaction of a single particle with the fluid. Now this is the interface of the Rocky software, as can be seen. Now these are the sections that I already explained previously, starting with the physics section. Now for the case, let's enter the gravity to be 80, minus 80 in the negative z direction, and the gravity start time will be 0, while the gravity stop time in my case the simulation time will be 20 seconds, so the gravity stop time should be more than that. It should be 22 seconds, so that the gravity will be stopped after the simulation is complete. The module section, obviously it's for particle-particle interactions, and it's not required in this particular case because my case is based only on a single particle. Now by default these are the geometries that are present in the Rocky software: the inlet, receiving conveyor, and conveyors. For my case I have to import custom geometry that I've made in the ANSYS Design Modular. a simple box like geometry, and it's exported it in the MSH mesh format. Now let me import it in the same dimensions. Now in this particular case, I have made the geometry in meters. Depending, obviously we have to be unit consistent. If we want to make a geometry in millimeters, we have to go for the same units throughout the case. Now this is the geometry. Let me show you. Now the background color, let the background color be white, and the font color should be black. Here we can adjust the views. Okay, now let's color the geometry so that it can be, we can see it. Now transparency should be 70% in this case. We can also adjust it to be 10% or 20%, whatever. Now here we can also enter the motion frame if we want to move the geometry, or if there is any motion required or necessary in the geometry. But in this case there is no, so I'm not. Also material, we can also define materials for the geometry, means the density of the geometry boundaries and anything like that. I'll explain that later, where we have to define that. Also now in this case the enable time for this should be 0, and the disable time, obviously I'll set it to be 22 seconds as well after the simulation time, and the simulation time is 20 seconds. This is the triangle. That triangle size is basically performs a triangular geometry by default in Rocky software on the boundaries. Obviously it's not required in the present case, it's only required in the cases when there are particle boundary interactions, so that we can calculate those things, and it basically creates an equilateral kind of triangles for the meshing. These are the nodes that I've already showed you. Now these are the sections, the mass, the where we can adjust the mass of the boundaries, the mass of the geometry to any value, means 1000 grams, 1000 kg, 100 kg, whatever we say. In this particular case I've changed it to many values, but it doesn't matter whatever, because there is no interaction of the particle with the boundary, and the geometry itself is only there to be filled with the fluid, but there is no interaction with the particles, so whatever we set the value, it doesn't matter. In the replication section we can replicate the geometry, means if we want to create multiple kind of these geometries, I can do that by replicating that. If we want to create any kind of conveyor, so we can do that as well. Now moving towards the motion frames, here we can adjust the any kind of motions in the geometry. In this case it's not required, so I'm not doing that. In the material section, as I said earlier, that we can define the properties, the materials of the particle, and the boundaries here. The boundary, this is what we can set it to any value, because again here the geometry is not involved, interaction with the particle itself, so we can set the value to any value, but we cannot set it to 0, because then the software will not run the simulation. Now in this case I have to set density for the particle, and that in the particular case is the density is 5. The Young's modulus, I cannot set it to 0, because these things and Poisson's ratio are required in the particle interactions, but there is no role they can play in this simulation. But I cannot set it to 0 again, because the software will not run the simulation. I have changed the values. I have changed the values multiple times, and it has no effect on this kind of simulation, because it's only a single particle simulation. In the material interaction also, it's not required in this case. Now in the particle section, let me introduce a single particle. That is by default a sphere. Let me change the view. Now let me import a custom particle for you. These are the particles by default present in the Rocky software, but now I want a custom particle. There are different particles that I studied during my research project. So I can import it as a custom polyhedron or any kind of custom particle. So like this is the particle. Wait a minute. This is the particle that I've made, the prolate particle, an ellipsoid that I've made in the ANSYS space claim, and I imported it as a STL format, importing it in the same dimensions as I made earlier. So this is the prolate particle. Okay, here we can change the size, orientation, movement, composition of the particle as well. Now here, this is the info. It gives the volume, area, and also the mass and position of the particle as well. Now the mass will be required later on. So let it 52.34. So now moving towards the input section, I'll use here a volume fill, not a continuous injection. At a specific location, I'll introduce the particle in the geometry. So let me show you now how it works. Now here I have to define the center coordinates. I wanted the particle to be at the center at the start of the simulation. So let it be this. In this particular case, these are the center coordinates, and the dimensions of the whole geometry are 12.8 and 25.6 meters. Obviously the highest in the z direction, because in this direction the particle will be dragged. These are the seed coordinates that I have already adjusted previously, so I'm doing this 12.8 and oh sorry, it's 6.4. No. Now here I have to introduce the particle. This is the particle 1 that I created. Now I have to enter the mass of the particle accurately, because if I enter it to be a value more than that, so let me show you how it works. If I set it to be 55, so 2 particles will be introduced. So I have to be sure of it that I am entering the exact value, the exact mass, 52.34. Now moving towards the next section, contacts. Obviously there is no particle-particle interactions. So now moving towards the CFD coupling section. For that I have to create the ANSYS file. That is a Fluent to Rocky file. F2R file is required for that. So let's make that file first. Now here, moving towards the Fluent 19.2, which is the required version that can be coupled with this version of Rocky. Okay. Okay, so double precision is required, a 3D geometry, and also it's serial processing. Now let's define the folder where the file should be saved. Now keep in mind one thing, all these files should be saved in a single folder, because the coupling will work only like this. If we save the files into different folders, it will the softwares won't couple. Rocky won't couple itself with ANSYS. All things should be saved in a single folder. The geometry and the coupling file, also the Rocky file as well. Now here I have to import the same geometry. That I imported in the Rocky software as well. This is the geometry.mesh that I've created in the ANSYS design modular. A simple box. It is a 3D box. I have to fill it with fluid so that I can introduce that fluid in the Rocky. The fluid side will be tracked by means ANSYS is used, Fluent is used for the Eulerian approach, while Rocky plays the part of the Lagrangian approach. Now here, moving towards the first section, the general section. Here, pressure-based approach. It's a steady state, not a transient case. I have to, the gravity should be same in both cases. In the z direction, it is minus 80. The gravity value for each and every simulation point should be same. Otherwise, the results won't be accurate. Moving towards the second section, models. Now here only one, because it's a simple one-way coupling case, so I have to track only the fluid. And for that viscous model, laminar flow is only necessary. Fluid. Now I have to introduce the properties of a specific fluid that is required in my case. So let me do it for you. Let I name it as let it be fluid, having a density of 1 and a viscosity of 5. Now let's save it. So it's successfully introduced. Now I have to introduce the fluid in the geometry. Now here by default here the material name is air. I'll change it to fluid because here I have to introduce the fluid in that. Now again moving towards the boundary condition now. Sorry, it's the wall domain. Obviously it should be a stationary wall and no slip boundary condition. Now moving towards the next one. It's not a dynamic mesh and the reference value is obviously not required. Moving towards the methods, it's by default using simple algorithm and that's okay with it. Moving towards the next section, that is residuals. Now I can, if one wants to set it, it matters if we increase the residuals or not, because the results are almost the same, but I want to do it, so if anyone wants to do it, he can do that. In both cases, the residuals, changing the residuals doesn't matter that much. Results will be accurate in both the cases. Now hybrid initialization. Let's initialize the case first and moving towards the calculations. Number of iterations, let it be 100. Obviously it's a simple case, so the calculation is complete within a one single iteration because there is only fluid. Now I have to export this fluid for Rocky so that I can introduce it in the Rocky software for the fluid particle interaction. Now this is the way to export it. When we install the Rocky software, a plugin with this kind with the specific ANSYS version will automatically be installed. Export solution to Rocky, which is the F2R file, Fluent to Rocky file. Now let's save this case as well. Let it be of the same name, prolate. Now exit. Okay, so these are the three files that are exported, and the required file for coupling is the Fluent for Rocky file. This is the file that is required for coupling. Now let's move to the coupling section. Now let's it be Fluent one-way steady state. Obviously it's present in the same folder, so Fluent for Rocky F2R. Open. Now here multiple correlations are present in the Rocky software. Obviously they are required as an initial guess so that we can move to the calculation as the drag law. Let it be has Levin spill correlation. Now there many people will be concerned that whether it gives results similar to Heather and Levin spill or not. Many people will be concerned regarding the accuracy of the DEM-CFD, so I'll explain it later on. Now moving towards the domain settings, the minimum and maximum values of the geometries will be set here. The maximum values are 12.8 and the minimum values are zeros, obviously 25.6. So the whole domain is covered here, as can be seen. Now the periodic boundary conditions are required in the z direction because the particle will be tracked in that direction. So here I have to set that as well, 12.8, 12.8 and again 25.6 meters. Now the last section is solver. Here I can set the duration of the simulation, and the output frequency here stands for the interval between data points that I want. For example, if I want, in this case, 0.05 second, I want each and every data point after 0.05 second. And these sections are related to particle-particle interactions and regarding the CPUs, that how many cores I want to use. So I'm not going into that now. Collisions. In the advanced section, we can also set the time step. Now, it can be automatic or we can set it manually. Now let's start the simulation. This is the end of the simulation. As can be seen, these are the results. Let me play the simulation for you. These are as can be seen, the translational velocity is changing until it becomes completely constant. Means the terminal velocity will be achieved, so that velocity will be used for calculating the drag coefficient. Now let me show you the results, how to compute the results in the Rocky software or plot a curve in the Rocky software. Moving towards the particle section, the properties. There are so many things here already present. We can plot each and everything. With respect to spatial coordinates and with respect to time as well, we can plot many things. Now here I want the translation z velocity, so let time plot, and the value is average. So this is the curve, and it can be seen it's completely saturated at the end. Starting it is minus 3.705. It's changing, still it's changing, it can be seen, but at the end it becomes constant. So this is the value that will be used for in the calculation of